Now let's turn our attention to what happens when our solute is also volatile, just like our solvent. It gets a little bit more complicated, of course. So let's start with the ideal solution, which I love that phrase because it sounds so lovely. It's ideal. So with it's an ideal solution, and that means that our solute and solvent interactions are very similar to our solvent solvent interactions. And so they would have the same intermolecular forces if the solvent particle was interacting with the solute or if the solvent particle was interacting with another solvent molecule, right? So in these situations, then we just take the sum of the partial pressures of each of the two solutions. So we take the sum of their vapor pressures. So that's the easiest. So really then that's just going to be the totals equal to the vapor pressure is equal to the vapor pressure of the solute plus the vapor pressure of the solvent. So that's going to look like so that vapor pressure for our solution is going to be this P total right here. And it's going to be equal to the partial pressure of the vapor pressure of our solute and the partial pressure of the vapor pressure of our solvent, right? So we really need to know like how much is our solute versus solvent contributing to our overall vapor pressure. And we're going to get that piece from our mole fraction of our solute times the vapor pressure of the solute. Like, so if I had a pure sample, so this with the little dot, the P with a dot, this is our vapor pressure of the pure substance. And the vapor pressure that we're talking about here, the pressure we're talking about here is going to be the vapor pressure of the pure solvent. And so that's going to be times the mole fraction of the solvent. And that's going to then give us, right here, that's going to give us our total vapor pressure for the solution. And so this is an extension of what we just did for the non-volatile solute, except we're going to do it for both the solute and the solvent rather than just the solvent and just add these two together. So again, this is when our solute and solvent interactions and our solvent-solvent interactions are really similar. That's not always the case. So in these non-ideal solutions, we've got two possibilities. First, we could have solute-solvent interactions that are stronger than our solvent-solvent interactions. And so in this case, when those solute-solvent interactions are stronger, the solvent is going to have more positive or more attractive forces between a solvent and a solute than a solvent and a solvent, right? So the solvent particles are going to want to stick around those solute particles. And so it's going to actually prevent some of the vaporization that occurs from the solvent. And we're going to see the vapor pressure decrease. Now, on the opposite side, we could also have solute-solvent interactions that are weaker than our solvent-solvent interactions. So in this case, the solvent has more attractive forces to the solvent than it does to the solute particles. And so in that case, putting solute particles into the solution disrupts those solvent-solvent interactions, gets in the way. It makes it easier for a solvent to actually vaporize, right? To go into the gas phase. And so we see the vapor pressure increase. So down here, we have our weak solute solvent interactions shown here, showing an increase in the predicted vapor pressure for an ideal solution. And we see a decrease here if we have stronger interactions than what we would predict for our ideal solution.